So first of all, thank for the invitation. Thank for being the last speaker. It is an honor. I have to close this wonderful 2 days of sub-Riemannian geometry. And actually, I will speak about rank 2 distribution. So this is a joint work with Andrei Agrachev, but it is actually a part of a bigger work that we are carrying out even with Antonio Lerario at CISA. And since the title is somehow difficult, I think, I will start from the very beginning with the settings. So I work in a connected smooth manifold. I choose a rank 2 subbundle in the tangent space, equiregular, so no problem with that, a perfectly smooth rank 2 subbundle. And well, I write I to mean the interval 0, 1. And then I fix a point, and I consider the set of admissible curve omega, which starts at the point x. And a curve for me is admissible if it is absolutely continuous, if its velocity belongs almost everywhere to the distribution f, and if gamma dot is L2 integrable. So once that you have required these 3 things, then you endow the space of curves omega with the W12 topology, and omega becomes an Hilbert manifold, right? Which is locally modeled on the space L2. Then you can define the endpoint map. You define a map F here that takes a curve and gives you back the final point of the curve, right? And if you choose another point y, which is different from x, you define omega y to be the pre-image of y via the endpoint map F. If you want, omega y is the fiber over the point y of F. Or if you want, omega y is the set of all admissible curves that join x and y. So if y is a regular value of the endpoint map, omega y is a smooth Hilbert submanifold. So essentially everything goes, let's say, fairly well. But otherwise, and unfortunately this is the typical situation, y is not a regular value, and omega y is an Hilbert submanifold with singularities. So a curve gamma, an admissible curve gamma, is a critical point. A curve gamma is a singular curve if it is a critical point of the endpoint map. And the corank of a singular curve is defined as the codimension of the image of the differential at gamma at F. So as the dimension of the space that you cannot cover at the first order with the differential. So from now on, I will just consider singular curves. And the purpose of my talk is to give, in this setting, a local description of the set omega y around the curve gamma. So I actually want to give you some intuition about how this space is made locally around the singular curve gamma. Later I will specify the class of curves that I will study, but later. So in general, there are problems to my project because df is not Fredholm. The point is that the kernel of the differential is infinite dimensional, and therefore the singularities of omega y are deep, and essentially the local geometry is inaccessible. So all the techniques of classical analysis usually fail. And the problem is that even in the simplest case, so even if d gamma has corank 1, then the Hessian has an infinite kernel. So even if you want to try to develop a second order theory, this is not possible because the situation is too degenerate. So really, the Hessian map has a huge kernel. Not even the second order theory tells you anything. And so you can ask, why do you want to study such a problem? Well, because, of course, the motivation is the classical one. Because if I endow my distribution with a Riemannian metric, I can define the energy. So the energy is basically the L2 norm of the velocity of the curve. I remark that the property of gamma dot being L2 integrable is independent of the metric. But once you have chosen the metric, then you can define the energy. And then I ask you, OK, solve me this problem. So find me the minima of the energy among the admissible curves that join 2 given points. And the fact is that singular curves might be minimizers. So, and this was proved in 1995 by Richard Montgomery, and it is to my opinion, the real starting point of sub-Riemannian geometry. And the fact is that the minimality of singular curves is not related to the functional that we are trying to minimize. So the question is, why are they minimal? I mean, it is a natural question. So as I told you, I need to restrict myself to a particular class of curves, which I call rank 2 nice curve. So I require for gamma these two properties. The first one is gamma is corank 1, strictly abnormal and regular. And then I ask that the final point is not a conjugate point along the curve. So I suppose that these two hypotheses are a bit technical, so let me explain a bit. Well, the first one, being of corank 1 and strictly abnormal, it is clear. You have essentially to apply the Lagrange multipliers rule to the pair fj. And then this is saying to you that the only abnormal covector has this form, up to scalar multiples. The regularity property means that essentially gamma dot can be recovered with the minimal number of differentiations possible. And this was a terminology introduced by Sussman and Liu in 1995. But if you want a practical definition, you take the extremal curve of covectors associated to the singular curve gamma. So essentially the curve in the cotangent space that starts at lambda, so the abnormal covector, and such that if you project it down to the base manifold, you get your singular curve. And then being regular means that this extremal curve belongs to the delta square orthogonal, but not to the delta cube orthogonal. Right? So you annihilate the second ordered bracket, but not the third one. And this is true for every time in 0, 1. And then I discuss a bit the notion of being non-conjugate. So basically you have to introduce the Hessian map, right? Which is a map which is defined from the kernel to the co-kernel, right? Such that if you multiply with the covector, you get a well-defined quadratic form on the kernel. So to ask that y is not conjugate is the same as to ask that the Hessian map is non-degenerate on this subspace V perp of gamma dot. Essentially, when you apply variations to a given curve, you can apply variation that simply reparameterize the curve, right? You can reparameterize the curve, and you imagine that these variations will be somehow in the kernel, because you're not changing really the curve. You're simply changing the velocity at which you are crossing the curve. So essentially, to restrict yourself to this space means that you want really to look at the variations that really displace you from the final. So the variations that really moves you from the original curve. Right? And, well, these other points are philosophical points, but let me tell you something. The notion of being regular is really similar to the notions of singular curves of minimal order that was introduced by Emmanuel, Fred, and Yassin in their JDG paper. And they proved that all singular curves are of minimal order for the generic distribution delta. And then once we choose such a curve, the set of non-conjugate points is dense along the curve. So all this is to say that I'm studying a very typical situation. So I'm studying the most typical situations for rank 2 distributions, except for a point, is that in fact, regular singular curves are not exactly the same, because in fact, if you require the regularity property, then you are implying that your curve satisfies the strong Legendre condition, and in fact that your curve is smooth, right? So, which is a big advantage in general. So now, let me put everything into coordinates. So I choose a local frame x1, x2 for delta, and I assume that gamma is an integral curve for the first vector field. This is possible, and this is safe, because gamma is smooth. So here, I'm using essentially that gamma is smooth. Otherwise, the rectification theorem does not work. And then, okay, I describe my admissible curves as integral curves of this differential system, right? So I'm basically centering everything at 1, 0, right? And in this way, I can reinterpret the endpoint map and the energy on the Hilbert space L2. And the correspondence between the two definitions is given in the following way. So f of V1, V2 is f of xi, where xi and V1, V2 are related by this differential equation. So if I write f of 0 in particular, I am looking at f of gamma. And then the energy has this forming coordinates, so it's the L2 norm of 1 plus V1 and V2. Fine. And then this is my theorem. So my theorem says, another point, sorry. So you see that in this way, essentially we are splitting L2 of 0, 1 into R2 into two copies of L2, right? So in some sense, the control space is L2 times L2. Here, this is a theorem. There exists a neighborhood which is contained in L infinity times L2. And a continuous map that goes from this neighborhood into L infinity times L2, which is a homeomorphism onto its image. So essentially, the map rho is a change of coordinates, right? And then once you have changed coordinates, you can construct an origin-preserving diffeomorphism such that D0 phi is the identity map, such that in a local system of coordinates induced by rho, you have the following expression. So f of phi essentially has the non-homogeneous term, so the constant. Then you have a degenerate linear map, because this map does not cover, let's say, the abnormal coordinate. And the abnormal coordinate is covered by this one. So this is a normal form, in fact. And in particular, you see that if you want to describe omega y on this smaller neighborhood, then you simply take all the pairs that lives in the kernel and such that they satisfy this property. So lambda times the Hessian applied to this v is equal to 0. So in some sense, I've reduced dramatically the complexity of describing this set. But then, I will discuss all the hypotheses of my theorem in a while. Let me just say that the choice of the space L infinity times L2 is intrinsic to my problem. So once I have chosen the rank 2 nice curve gamma, I can speak of L2 times of L infinity times L2. So it depends just on the choice of gamma, not on the basis, not on coordinates on M. So in this sense, it is intrinsic to the problem. Commentaries. Well, there are many hypotheses. None of them is by chance. So I'm telling you this because when I proved the theorem, I put hypothesis where I was able to prove the theorem. But then I realized that it was the only possible choice of hypothesis possible. So rho is just a continuous deformation. So my theorem is not a Morse lemma, because the Morse lemma does not have a deformation. You apply your isomorphism without changing coordinates. But my map here is necessary to cut out the kernel of the Hessian map. So first I need to reduce the degeneracy of the Hessian map. The degeneration of the Hessian map is too big, and to cut it out, I need an homeomorphism. I cannot do it with a diffeomorphism. But under some aspects, my theorem is even stronger than the Morse lemma, because it says, well, simply change coordinates, and then you really see how your set is made. So the situation in this case is really rigid. I mean, if you use appropriate coordinates, then you see what omega y looks like. And then, of course, it reduces omega y to a quadratic cone, so to the zero set of a quadratic form, because the theorem says this one. So this is a quadratic cone, right? An infinite dimensional quadratic cone. Fine.
See. So f is your endpoint map, right?
See.
The previous slide.
Previous slide.
But lambda is just a quadratic form, right? So
Yeah. So the only direction that is missing with the differential. So this one covers all but one direction.
Okay.
This one takes the last direction. Okay, so why the space L infinity times L2 is not by chance? Well, these are some known facts along regular singular curves, that if you cross the singular curve, you find just a finite number of conjugate points, because conjugate points are isolated, right? And whenever you pass such a point,
Okay, so we say goodbye.
we say goodbye to the leader.
Bye.
Ciao.
Go, Emmanuel. Bye-bye, guys. See you next time, maybe tomorrow. Bye. I think you can continue now. This interruption.
No, but it's fine. Come on.
5 more minutes.
Okay. No, fine. So whenever you pass a conjugate point, then, I mean, at a conjugate point, the kernel of the Hessian, so the restricted to the subspace that I was talking to, is of finite dimension. And whenever you cross such a conjugate point, the negative index of the Hessian map increases by exactly the dimension of this kernel. So essentially, at the end, you have your quadratic form as a negative eigenspace, which has the dimension equal to the sum of all the multiplicities along the curve. Right? So since you have a finite number of conjugate points, and at every conjugate point the multiplicity is finite, then at the end you have a finite dimensional space, negative eigenspace. So you can split your control space in this way. So this one is essentially the part diffeomorphic to the image of the differential. This one is the kernel of the Hessian map. This one is the positive eigenspace. This one is the negative eigenspace. And as I told you, n is finite. So I restrict myself to the complement of n, which is a space of finite codimension. And I know that even if I restrict myself to this space, the endpoint map is open if I use the L2 topology. In fact, F is open for every choice of LP times L2 or even LP times L2, as long as P, for example, is less than infinity. So L infinity is really the only topology in which you can prove such a theorem, because a normal form tells you that on one coordinates you can move just on the positive direction, for example, because we have removed the negative direction for the Hessian. So the Hessian now is either 0 or positive. You cannot go back and forth, right? Which contradicts the fact that your map should be open. So in some sense, my theorem is a generalization of the rigidity phenomenon, right, which was studied by Robert Bryant and Su in 93. And to conclude a bit with my discussion here, to introduce the problem, let me tell you something about the appearance of the first conjugate point. So essentially, I have two quadratic forms, the Hessian of the endpoint map, Q, and the Hessian of the extended endpoint map, Q hat, right? So since the abnormal covector is lambda 0, so it has no energetic part, the two forms have the same expression. But they are defined on different domains, right? Because the domain of this map is smaller than the domain of this map. So here you have the kernel of the differential of the endpoint map. Here you have the kernel of the differential of the endpoint map intersected with the kernel of the differential of J, which is smaller. And the indexes are related by this formula, right? So either they are equal or they differ by 1. And the difference is the following. You take the projection of the differential